Okay, I want to now try the open Feedwater heater, and this one's a little more complicated. So, an open Feedwater heater, we have a stream up here, and we take off some of that flow, and then we also have a stream coming back this way, and possibly a stream coming in here, and all those streams mix together and come out as a mixed flow. So we have 3 inlets and 1 exit, and let's see if we can model that. Now we're making some assumptions. Change in kinetic energy is equal to 0. Change in potential energy equal to 0. Steady state. That should take care, yeah, that should take care of everything. So we have dECVDT is 0, so equals, also we're going to say that Q is equal to 0. So our system boundary is on the outside of the box here. So all the heat transfers taking place inside, and also there's no work. So no power, no rate of heat transfer. So we have Q minus W, those two terms are 0, and we have summation m dot I HI. Since kinetic and potential are 0, I don't have the plus V squared over 2 in GZ, minus summation m dot E HE. So I simply sum all those terms up. My mass continuity equation, steady state, so dmCVDT is 0 equals summation m dot I minus summation m dot E. So let's look at trying to put this into a spreadsheet. So these are the equations we're going to use. Right, I'll come up here, and so this state coming in here is the state of this pipe. So nothing's changing over here. So this just equals that state. Nothing's changed. But coming back, this is the state of this return pipe, and coming out here it obviously changes. So we're going to make this state increment, that plus 1. Okay, now we need to calculate these properties here. So this is equal to water, and I'm given values for pressure and enthalpy. And I'm trying to find temperature. So pressure, comma, enthalpy. And that matches my value here. Now, you'll notice none of these properties are changing because all I did was take off some of the mass flow. So the only thing that will change will be the mass flow rate. So we just need to calculate the other two properties. And the quality. X equals, specify the pressure, equals X, the pressure, and the enthalpy. All right, now up here, this is the fraction of the flow that gets diverted, but the fraction isn't the fraction of this, it's the fraction coming into the, coming out of the first component. So if we look at our example here, the fractions are all from this maximum flow here. So this flow here is referenced in this big example. So I have it down here in this cell. So I'm going to reference that cell for this component. So I have this mass flow rate minus 5% of this, the total mass flow in the power plant. So I'm going to do this one first. So equals this minus 5%. So this 5% of this total flow rate. And that's just how we define the fraction of flow that's diverted. Instead of being a fraction here, it's the fraction of the maximum flow in the power plant. So that one's good. Everything else is pretty simple. This one just equals this, so that's a valid equation because nothing's changing. And if you grab the corner right here and drag that down to here, it will just copy that formula. So every cell here now is just the cell across from it. So all those look like they match. All right, now we can come down here. So we're trying to find the temperature. We have pressure and enthalpy. So again, equals water. Specify. Okay. Equals water. Pressure. It doesn't like that. Let's see. Type in something wrong. Equals water. Typo in the formula. For some reason, it's not letting me pick that cell. Because I'm trying to select the cell I'm supposed to be typing. A little carried away. I'm trying to pick them ahead of time. So type pH, not select them yet. And what I want is temperature. So pressure, comma, enthalpy. That's my givens. And I get 99.62, which matches my value over here. Do the same thing here. I could copy this. If I hit escape, come down here, click up here and paste, and then just change this to S. And then click here, paste, change this to, well, actually that's totally different formula. So X, and I specify the pressure and the enthalpy. So everything's matching so far. These values, since all of this flow is coming in here, this is passing what's remaining on. So we're going to put zeros here, since all of this returning flow comes back in. So now we have nothing passing on to the elements to the right. So these blue lines are keeping track of this blue pipe. And if we look at the example, there's sometimes where this blue pipe continues on to the right, but here then there's no flow coming into this pipe. So we're going to terminate it with some zeros. Right, now I need to calculate what's coming out. Now this requires us to come back and look at our expressions here. So let's label this state 4 and this state 7, and this we don't have a number for it, so I will see if we can get that from our example. So state 10, so usually I would call this state 11 and this state 12. So for this one, I'm going to call this state 12. It doesn't really matter. And then coming out of here then is state 8. Okay, so now going to use these equations to find what the mass flow rate at state so my m dot return here, I have it as a given, but I'm going to delete that. I'm not sure why that was there. It shouldn't be in yours. So I'm going to calculate what that is. So the mass flow rate at 8 equals, if I use this equation, so I've got 0 equals m dot 4 plus m dot 7 plus m dot 12. Those are my 3 inlets, minus the mass flow rate at the exit. This is the only exit, minus m dot 8 equals 0. So that means that this mass flow rate is the sum of all of them coming in. So the part that's coming in here is 5% of this, or the other way I can calculate it, it's what the difference in between these two values. So let me write the first one, m dot 4 is equal to this difference, this minus this, so that's what I subtracted off. So that's how this got to drop to 5 kilograms per second, because 5 kilograms per second went that way. Then plus whatever's coming here, plus whatever's coming here. So this is a mass flow rate of this coming here. So those are my three inlets, and then I'm bringing this to this side of the equation. So I'm solving for m dot 8. So that's my mass flow rate, and it turns out I'm back to 100. Of course, if this wasn't 85, then I'm not, but I'm going to leave that there as 85. So I'm back to 100% of the flow. So that one's done. And now I'm going to use this equation to solve for H8. So let's write that. 0 equals m dot times H for each inlet. So m dot 4 H4 plus m dot 7 H7 plus m dot 12 H12, and then minus m dot 8 H8. And this is the one I'm trying to solve for. So I'm going to bring that term over to this side of the equation. So get rid of that and have m dot 8 H8. Then I'm going to divide this whole side of the equation by m dot 8. And I'll have my enthalpy for state 8. So H8 equals m dot 4. So what's coming in here again is this minus this times the enthalpy of this. I can get it from here or here. I'll go ahead and grab it from here, I guess. Plus m dot 7, which is this, times H7, plus, I've sent that value in already multiplied, so this is m dot times H. So that's this one. They've already been multiplied together. And then that sum of those quantities divided by the mass flow rate of 8, which is this total here. And didn't like something. Oh, I need an extra parenthesis for my numerator. There we go. So I put these terms, this minus this, in parentheses, but I still need one for the end of the numerator. I get 618.55. All right, now I need some other property. Well, an open feed water heater, all the pressures are the same. So the pressure is known. So whatever pressure this is, it's the same, or I could get the pressure from up here. So I'll go ahead and grab it from here. And actually, I think I like this not being yellow. So then I can change those two individually. So I'm going to return that to white and get that from here. So this is a calculated one, which is whatever that pressure is. So now if I change this to 1200, then all my pressures change. Right, so now I know pressure and enthalpy. So again, I could copy this, put it over here. Now that's different than the value. What I'm copying is the formula, so it actually moves those. And then because these two were copied from these other givens, I can copy those over here. Just a little shortcut. So you can double check those. So pressure and enthalpy, I'm trying to find entropy. There's my pressure and enthalpy here. And then the quality is based on this pressure and this enthalpy. And I check my values and everything looks good. And I think I've got my open feed water heater functioning. So if you were to change this value, let's say to 0.2, to 0.1, let's say, then you should see all these values changing accordingly. 1200, and everything should change like that. I'm going to undo those two just so I get back to the ones that match here.